Hyperbola?
In the year 1911, Ernest Rutherford's experiments with atoms showed that when one positively charged particle approaches another, it is repelled along a path shaped like a hyperbola.
So two positive particles just naturally repel each other. Eh, Charlie?
That's right, Ed. Maybe that's why you're starting to get on my nerves.
We've seen the plane slice the cone to produce a circle, an ellipse, and a parabola. If the angle is increased even more, the plane will finally cut through both halves of the double cone to give a hyperbola. The general shape of the hyperbola is much like that of a parabola. In fact, without the other half of the hyperbola, it might be difficult to tell them apart. But there is a fundamental difference in their curvature that is revealed when we examine the hyperbola's equation. One of the simplest hyperbola equations is y squared minus x squared equals 1. Writing this equation as y squared equals x squared plus 1, we can solve for y itself. Let's examine the positive upper half. When x is 3, then x squared plus 1 is 10, and the root is about 3.16. When x is 4, x squared plus 1 is 17, and the root is 4.12. As x becomes larger and larger, the value of y gets closer and closer to x. This is because the plus 1 is becoming far less significant than the large x squared. As x gets larger, the equation approaches y equals the square root of x squared, which is x. The true y equals x graph is this straight line. Plotting more points on the hyperbola, we see that as x gets larger, the hyperbola approaches but never touches the y equals x line. There's always that little plus 1 in the equation to keep them apart. The straight line y equals x is called an asymptote. Hyperbolas always approach asymptotes. Parabolas don't. They curve away from any asymptote drawn. The points where the two halves of the hyperbola are closest are called the vertices of the hyperbola. Hyperbolas can be narrow or wide and lie anywhere on the Cartesian plane, but they all have some properties in common. The major or transverse axis is defined as the line that joins the two vertices. The perpendicular bisector of the transverse axis is called the conjugate axis, or the minor axis. We can assign a length to the two axes by constructing a rectangle that's bounded by the vertices and has the asymptotes for diagonals. In this case, the lengths of the two axes are equal. We've seen that the distances from any point to the two foci always differ by the same amount. The length of the transverse axis turns out to be equal to this constant difference. This is one of the two standard positions in which we find hyperbolas. In the other standard position, the transverse axis is horizontal. One way of looking at this position is as a reflection of the first position in the line y equals x. Now the equation of any graph, reflected in the line y equals x, is simply the old equation with the x and y switched. The asymptotes remain the same, but now the transverse axis joining the vertices is along the x-axis. We can apply other transformations to the original hyperbola as well. Take a simple dilation, t mapping x and y onto 3x, 4y. This stretches the graph horizontally by a factor of 3 and vertically by a factor of 4. To find the new equation, we apply the opposite rule established in the last program. We are multiplying x and y by the factors 3 and 4 in the dilation. So we simply divide by those factors in the equation, x over 3 and y over 4. These factors provide the boundaries of the rectangle, the x boundaries, and the y boundaries. The asymptotes are simply the diagonals. The general equation possesses the same properties. We have a hyperbola in standard position, x squared over a squared minus y squared over b squared equals 1. The vertices are at a and negative a, and the length of the transverse axis is 2a. B indicates the vertical limits of the rectangle and provides the length of the conjugate axis, 2b. The equations of the asymptotes can actually be determined directly from the general equation. They are y equals bx over a and y equals negative bx over a.
Asymptote. Asymptote. That's such a strange sounding word.
Well, Ed, it's just Greek for not falling together.
That figures. I think I'm starting to fall apart myself.